Welcome! In this session, we will explore problem number 1170, titled Compare Strings by Frequency of the Smallest Character. Together, we'll break down the problem, analyze different approaches, and guide you toward an optimal solution. Let's dive in. In this problem, we are working with two string arrays, queries and words. For each string in these arrays, we define a function fs that calculates the frequency of the smallest character in the string. For example, if the string s is deci, the smallest character is c, which appears 2 times, so f deci equals 2. Similarly, if s is AAA, the smallest character is a, and it appears 3 times, so f AAA equals 3. The goal is to compare each query string in queries with all the words in words and count how many words have an fs value that is greater than the fs value for the query string. The result will be an array where each element represents the count of such words for the corresponding query string. The input consists of 2 arrays, queries, and words. Both arrays have a length between 1 and 1000, and each string within these arrays is composed only of lowercase English letters. The length of any individual string is between 1 and 10. The output is an array of integers where each element corresponds to a query string. Specifically, the ith element of the output array represents the number of words in words for which f, q, is less than f, w, where q is the ith query string. To better understand, let's look at some examples. In the first example, queries contain cbd and words contain zaz. For the query cbd, the smallest character is b, which appears once, so f cbd equals 1. For the word zaz, the smallest character is a, appearing 3 times, so f zaz equals 3. Since f cbd is less than f zaz, the count for this query is 1, resulting in an output of 1. In another example, queries contains bbb and cc, and words contains a, aa, AAA, and aaa. For the query bbb, the smallest character is b, which appears 3 times, so f bbb equals 3. Among the words, their smallest character frequencies are 1, 2, 3, and 4. Only one word, AAAA, has f, w, greater than 3, so the count for BBB is 1. For the second query in the same example, CC, the smallest character is C, which appears 2 times, so f, CC, equals 2. Among the words, their smallest character frequencies remain the same at 1, 2, 3, and 4. This time, 2 words, AAA and AAA, have f, w, greater than 2. Therefore, the count for CC is 2, resulting in an output of 1, 2. In another example, queries contains an ABC, and words contains B, BB, BBB, and BBBB. For the query a, the smallest character is a, appearing once, so f, a, equals 1. All words have smallest character frequencies of 1, 2, 3, and 4, respectively. Since all of these values are greater than 1, the count for a is 4. For the second query in this example, ABC, the smallest character is also a, which appears 1 time, so f, ABC, equals 1. Again, all words have the same smallest character frequencies of 1, 2, 3, and 4. As before, all of these values are greater than 1, so the count for ABC is also 4. The output for this example is 4, 4. Moving on to constraints, the problem guarantees that the lengths of queries and words are up to 1000, and the length of each string is up to 10. Strings consist only of lowercase letters, and this ensures that we can calculate fs efficiently within the given limits. There are some additional notes to consider. First, queries and words will always contain at least one string, so there are no edge cases involving empty input arrays. Second, when dealing with single character strings, the comparison is straightforward since fs is simply the frequency of that single character. Third, for strings where all characters are the same, the smallest character frequency is equal to the total length of the string. Lastly, with the maximum input sizes of 1000 strings of length 10 for both queries and words, it's crucial to compute fs and perform comparisons efficiently to meet the performance requirements of the problem. To solve this problem, we first considered the brute force approach. This method is the most straightforward. For each string in both the queries and words lists, we compute the frequency of its smallest character, denoted as fs. Then, for each query string, we compare its f, query, value against the f, word, values of all strings and words. Finally, we count how many f, word, values are greater than f, query, and store the result for that query. While this approach is simple to understand and implement, it is computationally expensive. Calculating fs for all strings involves processing the total number of characters, which is O, L, and comparing each query to every word results in an O, Q asterisk W, complexity, where Q is the number of queries and W is the number of words. This makes the overall time complexity O, L plus Q asterisk W. Such an approach becomes inefficient as the size of the inputs grows, especially when there are many queries or words, or when the strings themselves are long. Therefore, we need a more efficient solution, which leads us to the optimized approach. Now, in the optimized approach, we focus on pre-computing and sorting to reduce redundant computations. First, we calculate the word values for all strings in the words list and sort these values in ascending order. Sorting ensures that we can use binary search to quickly determine how many word values are greater than a given query. For each query, we compute query and use binary search, provided by Python's bisect module, to efficiently count the number of words with word exceeding query. This reduces the comparison step significantly. The complexity here is improved. Pre-computing and sorting words takes O, W asterisk log, W, and for each query, the binary search operation is O, log, W, resulting in an overall complexity of O, L plus W asterisk log, W, plus Q asterisk log, W. This approach balances efficiency and scalability, but it does require sorting and a more advanced binary search implementation, which adds some complexity compared to the brute force method. An alternative optimization we considered is based on bucket frequency counting. In this approach, we leverage the fact that fs values are bounded by the smallest character's frequency in a string. This allows us to pre-compute a frequency array of size equal to the maximum possible word value plus 1. For every word in words, we compute word and populate the frequency array. Next, we transform this array into a cumulative frequency array, where each index represents the count of words with word greater than or equal to that index. This cumulative array enables us to directly retrieve results for any query. For each query, we simply compute query and look up the pre-computed result in constant time. This method is highly efficient, with a complexity of O, L plus W plus Q. However, it relies on the assumption that fs values are bounded, which may limit its generalizability to other problems. While it's the fastest approach, it trades off robustness for speed. After evaluating the options, we chose the optimized approach that combines pre-computation and binary search. This method strikes a balance between simplicity and efficiency. By pre-computing and sorting words, we minimize repetitive computations, reducing the workload during query processing. Sorting introduces a one-time cost of O, W asterisk log, W, but the binary search ensures that each query is processed in O, log, W, making this approach significantly faster than brute force for large datasets. Additionally, this strategy is versatile, as it does not rely on constraints like bounded frequency values, unlike the bucket frequency counting method. This means it can handle variations of the problem more robustly. While sorting does add complexity compared to the brute force approach, the performance gains for large inputs make it the most practical and scalable solution overall. This balance of efficiency, scalability, and ease of implementation is why we selected this strategy. In this problem, we are tasked with comparing two lists of strings, referred to as queries in words. For each string, we define a function fs, which calculates the frequency of the smallest character in the string based on lexicographical order. For example, if the string is apple, the smallest character is a, and it appears only once, so apple equals 1. The goal is to determine, for each string in the queries list, how many strings in the words list have an fs value that is strictly greater. To solve this, we start by parsing the input and defining the function fs. This function works by iterating through the characters of a string, identifying the smallest one, and then counting how many times it appears. Next, we pre-compute the fs values for every string in the words list and store these results in an array called words_frequency. For instance, if the words list is ABC, the smallest character in all strings is a, and its frequency is 1 for each, so words_frequency becomes 1, 1, 1. By pre-computing these values, we eliminate the need for redundant calculations later, improving efficiency. The next step is to sort the words_frequency array in ascending order. Sorting is crucial because it allows us to efficiently compare values using binary search later on. For example, if words_frequency initially contains 1, 3, 2, sorting transforms it into 1, 2, 3. With this sorted array, we can proceed to process the queries. For each string in the queries list, we calculate its fs value. For instance, with the query cat, the smallest character is a, which appears once, so f, cat, equals 1. To determine how many elements in words_frequency are strictly greater than this value, we use binary search. A helper function identifies the first index in the sorted array where elements exceed f, query. The count of elements greater than f, query, is then the difference between the length of words_frequency and the index found. This approach avoids the inefficiency of iterating through the entire array for each query. Finally, we store the results for all queries in an array called results and return it. For example, if queries equals cat, apple, and words_frequency equals 1, 2, 3, then f, cat, equals 1, and two elements, 2 and 3, are greater than 1. Similarly, for apple, f, apple, equals 1, and 3 elements, 1, 2, 3, are greater than 1, so the results array becomes 2, 3. The key insights in this approach involve optimizing both computation and comparisons. By pre-computing the fs values for all strings in the words list and sorting the results, we prepare the data for fast lookups. Binary search is used to efficiently find the index of the first element in words_frequency that is greater than f, query. This reduces the time complexity of the comparison step significantly compared to a linear search. It's also important to handle edge cases appropriately. For instance, if either queries or words is empty, the result should simply be an empty array. Additionally, if all strings in the words list have the same fs value, the comparisons depend on whether f, query, is smaller, equal to, or greater than that value. Finally, the solution relies on specific data structures, an array to store the pre-computed fs values, another sorted array for binary search, and the results array to store the output for each query. Analyzing the time complexity, the pre-computation of fs values for all strings in the words list takes m*k, where m is the number of words and k is the average length of a word. Sorting the words_frequency array requires m log m, and for each query, binary search takes log m. Within queries, the total cost for processing queries becomes n*log m. Combining these, the overall time complexity is m*k plus m log m plus n log m. In terms of space complexity, the primary overhead is the m space needed to store the words_frequency array. To illustrate how the algorithm works, consider the example where queries equals AA and words equals AAA, BBC. First, we compute fs for the words, resulting in words_frequency equals 3, 2, 1. Sorting this array gives 1, 2, 3. For the first query f equals 1, and binary search identifies two elements, 2 and 3, as greater than 1. For the second query AA equals 2, and binary search identifies one element, 3, as greater than 2. Thus, the output is 2, 1. This solution solves the problem using a combination of pre-processing and efficient search. Let's break it down step by step. 1. Imports. The bisect module from Python is used for binary search. It allows us to efficiently count how many elements in a sorted list exceed a given threshold. 2. Helper function fs. This function calculates fs for a string. It determines the lexicographically smallest character in the string using min.s, and counts its occurrences using s.count. 3. Pre-processing words. For the words list, we compute the value of fs for each string and store these frequencies in a list called word_frequencies. This list is then sorted, enabling binary search operations. 4. Processing queries. For each string in queries, we calculate its fs value. Using the bisect_right function, we efficiently count how many elements in the sorted word_frequencies list are strictly greater than the query's frequency. This count is derived by subtracting the position returned by bisect_right from the total number of elements in the list. 5. Result compilation. The counts for each query are stored in a result list, which is returned as the final output. Hashtag efficiency. Calculating f(s) for a string takes o(m), where m is the string length. Sorting word_frequencies takes o(n) log n, where n is the number of words. For each query, binary search on a sorted list takes o log n. Thus, the overall complexity is dominated by o(n) log n plus q asterisk log n, where q is the number of queries. Hashtag edge cases. Empty queries or words lists are handled by returning an empty result list. Strings with repetitive characters, e.g., AAA, are processed correctly, as min, s, and count operate independently of string length. This implementation is efficient, concise, and handles all edge cases effectively, making it suitable for competitive programming scenarios. On this slide, we begin with the implementation of the solution in Java. First, we define a helper method called calculateFrequency, which calculates the frequency of the smallest character in a given string s. To achieve this, we initialize smallest char to z and a counter count to 0. We then loop through each character in the string. If the current character is smaller than smallest char, we update smallest char to this new character and reset the count to 1. If the current character is equal to smallest char, we simply increment the count. This ensures that by the end of the loop, we have both identified the smallest character and counted its occurrences. The method then returns this frequency. Next, in the number smaller by frequency method, we start by creating an array word frequencies to store the frequency values for all the words in the words array. Using a for loop, we calculate the frequency of the smallest character for each word by calling calculateFrequency and store the results in the word frequencies array. Here, we continue the implementation by sorting the word frequencies array. This sorting step is important because it allows us to efficiently use binary search later to find counts of frequencies that are greater than a given value. After sorting, we initialize a result array to store the output for each query. Next, we process each string in the queries array. For every query, we calculate the frequency of its smallest character using the calculateFrequency method. Once we have this value, we use a helper method called binarySearch to determine how many frequencies in the word frequencies array are greater than the current query's frequency. The result of this count is then stored in the corresponding index of the result array. Finally, after processing all queries, the method returns the result array. At this point, the binarySearch method is introduced, which is used to efficiently count frequencies greater than the target value. In this final part of the implementation, we complete the binarySearch method. The goal of this method is to find the first index in the frequencies array where the frequency is strictly greater than the target value. We use a standard binary search approach with a left pointer initialized to 0 and a right pointer set to the length of the array. Inside the while loop, we calculate the midpoint mid and compare the frequency at this index with the target. If the frequency at mid is less than or equal to the target, we move the left pointer to mid plus 1. Otherwise, we move the right pointer to mid. When the loop exits, the left pointer will point to the first index where the frequency is greater than the target. The method then returns the count of such frequencies, which is calculated as the total length of the array minus the left pointer value. This concludes the implementation, ensuring that the solution is both efficient and easy to follow. To solve this problem, we start with the given example where the queries array is CBD and the words array is ZAZ. The first step is to calculate the frequency of the smallest character, f(s), for each word in the words array. Here, for the word ZAZ, the smallest character is a, which appears 3 times. So, f ZAZ equals 3. The word frequencies are stored as a list, which in this case is 3. Next, we sort these frequencies to make them ready for binary search, but since there's only one frequency, the sorted list remains 3. Afterward, we process each query. For the query CBD, the smallest character is b, which appears 1 time. Hence, f CBD equals 1. Using binary search, specifically the bisect_right function, we determine how many word frequencies are greater than 1. The index returned by bisect_right, 3, 1, is 0, and the count of frequencies greater than this value is calculated as len, word_frequencies, index, which gives us 1. Therefore, the result for this query is 1. The final output for this example is 1. Now, we move to the second example with queries, BBB, CC, and words, AA, AAA. First, we calculate the F, S values for the words. For A, the smallest character is A, which appears once, so F, equals 1. Similarly, for AA, the smallest character appears 2 times, giving F, AA, equals 2. Finally, for AAA, the smallest character appears 3 times, so F, AAA, equals 3. This results in a word frequencies list of 1, 2, 3. After sorting, the list remains 1, 2, 3. For the first query, BBB, the smallest character is B, which appears 3 times. Thus, F, BBB, equals 3. Using binary search, we find how many word frequencies are greater than 3. The bisect_right function on 1, 2, 3, with the value 3 returns an index of 3, meaning no frequencies are greater than 3. The count is calculated as len word_frequencies index, which equals 0. We append this result, giving us a partial result list of 0. For the second query, CC, the smallest character is C, which appears 2 times. This gives F, CC, equals 2. Using binary search to find frequencies greater than 2, we call bisect_right, 1, 2, 3, 2, and get an index of 2. The number of frequencies greater than 2 is calculated as len word_frequencies index, which equals 1. We append this result, updating our result list to 0, 1. The final output for this example is 0, 1. In the third example, we have queries, Z, and words, B, BB, BBB. First, we calculate F, S, for the words. For B, the smallest character is B, which appears once, so F, B, equals 1. For BB, the smallest character B appears 2 times, giving F, BB, equals 2. Finally, for BBB, the smallest character B appears 3 times, so F, BBB, equals 3. The word frequencies are 1, 2, 3. After sorting, the list remains 1, 2, 3. For the first query, the smallest character is A, which appears 1 time. Hence, F, equals 1. To find how many word frequencies are greater than 1, we use bisect_right, 1, 2, 3, 1, which returns an index of 1. The count of frequencies greater than 1 is len word_frequencies index, which equals 2. We append this result, resulting in a partial list of 2. For the second query, Z, the smallest character is Z, which appears 1 time. This gives F, Z, equals 1. Using binary search to find frequencies greater than 1, we call bisect_right, 1, 2, 3, 1, and get an index of 1. The count of frequencies greater than 1 is len word_frequencies index, which again equals 2. We append this result, updating our result list to 2, 2. The final output for this example is 2, 2. The time complexity of our solution is determined by several key operations. First, we calculate the function f, s, for each word in the words list. This involves finding the smallest character in the word using the min-s operation, which takes O, m, where m is the length of the word. Then, we count the occurrences of that smallest character using the s.count, smallest_char method, which also takes O, m. As a result, computing f, s, for a single word takes O, m, and for n words, this step adds up to O, n asterisk m. Next, we sort the word_frequencies list, which stores the frequencies of the smallest characters from all the words. Sorting a list of size n requires O, n asterisk log, n, time. Together, these two steps form the first parts of our overall time complexity. Now, let's consider the time complexity for processing the queries. For each query, we compute f, s, just like we did for the words. If the query length is k, this computation takes O, k. After that, we use the bisect_right function to perform a binary search on the already sorted word_frequencies. Since binary search has a time complexity of O, log n, processing a single query requires O, k plus log n. With q queries in total, this step contributes O, q asterisk, k plus log n to the time complexity. Combining all these components, the overall time complexity of the solution is the sum of O, n asterisk m, for computing f, s, on the words, O, n asterisk log n, for sorting, and O, q asterisk, k plus log n for processing the queries. This simplifies to O, n asterisk m plus n asterisk log n plus q asterisk k plus log n. For the space complexity, we start with the storage required for the word underscore frequencies list. This list holds the frequency of the smallest character for each word, so its size is proportional to the number of words, requiring O, n, space. Next, we consider temporary storage used during the computation of f(s). This involves storing intermediate results like the smallest character and its frequency, which only require O(1) space per function call. Finally, we have the result list, which stores the output for each query. With Q queries, this list takes O(q) space. When we combine these, the overall space complexity is dominated by the storage for word underscore frequencies and result, resulting in O, n plus q. To highlight the efficiency of the optimized approach, let's compare it to a brute force method. A naive solution would involve directly comparing the frequency of the smallest character for each query against every word. This requires O, q asterisk k, for calculating f(s) for all queries, O, n asterisk m, for calculating f(s) for all words, and O, q asterisk n, for comparing each query to all words. The total time complexity for this brute force approach is O, q asterisk k plus n asterisk m plus q asterisk n, which is inefficient due to the O, q asterisk n term from the comparisons. In contrast, our optimized solution reduces the comparison cost by sorting the word underscore frequencies and using binary search. This reduces the overall complexity to O, n asterisk m plus n asterisk log n plus q asterisk k plus log n. Importantly, both the best and worst case scenarios for the optimized solution have the same complexity because sorting and binary search dominate the runtime regardless of input. The big O notation for our solution is well supported by the algorithm design. Sorting the word underscore frequencies list dominates the runtime when the number of words, n, is large, contributing O, n asterisk log n to the time complexity. Additionally, binary search ensures efficient query processing, adding O, q asterisk log n for q queries. Together with the other terms, these components capture the overall complexity as O, n asterisk m plus n asterisk log n plus q asterisk k plus log n. This precise breakdown confirms that the big O bound accurately reflects the performance of the algorithm under different input sizes. When solving this problem, there are several common mistakes to watch out for. First, incorrectly calculating fs is a frequent issue. Remember, fs is the frequency of the smallest character in the string, and the smallest character must be determined based on ASCII values. For instance, a and a are not equivalent, so case sensitivity matters. Another mistake involves using inefficient nested loops for comparisons. If you directly compare each query frequency with all word frequencies, the solution can quickly become computationally expensive, especially for large input sizes. Instead, consider pre-computing and reusing data to optimize your approach. Misunderstanding the constraints is another pitfall. Constraints like the maximum string length or the number of queries and words are there to guide you in crafting the most efficient solution. Overlooking these can lead to inefficiencies or incorrect results. Off-by-one errors in comparisons are also common, such as failing to correctly count the number of words with frequencies greater than f, queries, I. Always double-check your indices and conditions in these comparisons. Finally, don't ignore edge cases. Scenarios like empty strings, single-character strings, or strings with duplicate characters in queries or words can lead to runtime errors or incorrect outputs. Testing thoroughly for these edge cases is crucial to ensure your solution is robust. Now, let's discuss some key insights for tackling this problem in an interview setting. First, it's essential to thoroughly understand the problem statement. Interviewers are often interested in your ability to break down a problem into clear, actionable steps, so take the time to fully grasp what fs represents and how the comparison should function. Once you've explained a brute force solution, focus on ways to optimize it. For example, you can pre-compute f, words, and sort them, enabling you to use binary search for faster comparisons. This demonstrates your ability to think critically about efficiency. Communication is another critical aspect. Walk through your thought process clearly, particularly how you calculate fs and perform comparisons. This shows attention to detail and clarity of thought. Additionally, always discuss edge cases, even if the interviewer doesn't ask for them explicitly. Being proactive in identifying potential issues with empty strings, single character strings, or edge case scenarios indicates a thorough and thoughtful approach to problem solving. Finally, let's explore related problems and alternative approaches. Some similar problems you might encounter include LeetCode 820, which focuses on the short encoding of words, LeetCode 49, which deals with grouping anagrams, LeetCode 451, which sorts characters by frequency, and LeetCode 692, which identifies the top K frequent words. These problems share overlapping concepts and can help you build a stronger foundation. Regarding alternative approaches, the brute force method is the most straightforward but becomes inefficient for larger inputs due to its n² time complexity. A better approach involves pre-computing f words and sorting them, so you can use binary search to count words with f w greater than f q. This reduces the time complexity to n log n. Another option is a hash map approach, where you store frequency counts of f words. For each query, you calculate f q and sum the frequencies of keys greater than f q, striking a balance between time and space efficiency. Lastly, if the range of fs values is limited, for example, when only lowercase letters are involved, you can use bucket sort to pre-process f words. This avoids sorting entirely and achieves an n time complexity, making it the most efficient method when applicable. To wrap up, we reviewed how to solve problem number 1170, focusing on comparing strings by frequency of their smallest characters. We discussed the intuition behind the solution, its complexity, and key takeaways for future problems. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!